Hi everyone, this is Dr. Hong. In this chapter, we are going to study about conjugate beam method. Conjugate beam method is very simple but very convenient method to calculate deflection. And what is deflection first? As you learned in 301, deflection is vertical displacement of beam or any other structure from original position. And what is deflection angle? Deflection angle is tangent of the deflected shape. We call it elastic curve and horizontal reference line. We are going to express it using degree or radian. So in the first page, let's learn or review what was definition of deflection, in this case vertical deflection, and deflection angle. Okay, deflection and elastic curve. Deflection of structures are caused by mainly from loads. And sometimes, if temperature fluctuates, then it may cause stress and resulting deflection. If there is a fabrication error, deflection may occur. Or settlement of foundation may cause deflection. Deflection must be limited in order to prevent cracking of brittle materials. For example, if you have a window right underneath the beam, and when beam is deflected, the window is very, very brittle and very weak, so it will break. So to prevent that kind of situation, we need to limit the deflection of beam. And sometimes you may feel the cantilever, reinforced concrete cantilever structure vibrate, and you do not feel good with the vibration. So it will vibrate or deflect too much, so that you do not feel comfort on that vibrating element. But those are not really strength issue, so that we are going to call it serviceability. The opposite concept of serviceability is strength issue. So we have two limit state, serviceability limit state and strength limit state. Serviceability limit state is not related to collapse of building, but anyway, occupants may not like it. So we have two issues, serviceability issue and strength issue. Most importantly, deflection is required to be calculated to analyze indeterminate structures. So this is our first step to come up with additional equation, additional exact equation using deflection for indeterminate structures. So in this topic, we are going to call the deflected shape of beam or any other structure, we are going to call it as elastic curve. Why is that? Because in the scope of undergraduate level of any course, structural engineering courses, we are going to limit our discussion within a linear elastic limit, so that any portion of structure will be elastic, not plastic. So if your structure or beam will be in plastic region, the curve or the deflected shape of beam or structure will be different from what we are discussing here. so that we are going to call the deflected shape of beam in this class elastic curve. Okay, let's look at support condition and the associated deflected shape. If it's roller, then slope will occur, even though deflection may not occur there unless you have settlement of foundation, but you are going to have deflection angle there. A pin, the same. We have deflection angle, even though we do not have deflection there. How about fixed support? If you recall starting statics, I asked you to view cantilever as extended into and behind the support location, so that because of that continuity, there will not be any deflection angle there. In this case, deflection angle will be 0 for fixed support. Alright, and we have discussed about the difference between rigid connection and fixed connection so many times, but still textbook says fixed connected joint. That is not correct term. Okay, that is not correct term, but this must be rigid connection. In rigid connection, fixed connection will not rotate, but rigid connection will rotate. But rotational angle will be the same in any rigid connection. As you see here, fixed connection, there will not be any rotation, so that deflection angle will be 0. But in rigid connection, like in frame beam to column connection, it will rotate, but rotational angle will be the same. If it's pin connected, of course, it is not rigid, so I would call it non-rigid connection. In non-rigid connection, rotational angle of column and rotational angle for beam will not be the same. Okay, and we learned that when you have bending moment diagram, in this case we are going to have bending moment diagram like this, and this is positive and this is negative. If it's positive, concave bending, and if it's negative, convex bending. And where sign of bending moment diagram switch from negative to positive, positive to negative, there will be inflection point. And we discussed about inflection point before, so that let me skip that. Okay, this is a typical elastic curve of the beam of several, and please memorize several deflected shape, which is elastic curve. Here we have deflection angle. Here we do not have deflection angle, which is 0. And all other shapes are there, and you may want to draw several times so that you can memorize. It will help a lot, and it will help prevent any possible mistake in applying analytical method. Okay, now conjugate beam method. This conjugate beam method is based on similarity of equations. Similarity of what? Let's take a look at one by one. When we do bending moment diagram, we learned that if you differentiate shear force once, then you are going to get load. And if you differentiate bending moment diagram, then you are going to get shear force. So that first derivative of shear force will be load. Second derivative of bending moment is load. Of course, load must be continuous. If it's not continuous, like concentrate load, then you need to subdivide into two things because they are not continuous and we need to use piecewise function mathematically. Okay, we reviewed about bending moment diagram. Now, conjugate beam method. We are going to use a similar relationship between load, shear force, and bending moment. Okay, here, deflection angle theta, and if you get first derivative of deflection angle theta, then you are going to get m over EI. M is bending moment, as you saw here. This one the same. And E is modulus of elasticity, if it's still 29,000 KSI. And I is moment of inertia. And from now on, you are going to see EI goes always together. And then, how can you interpret EI? Okay, let's look at E as material stiffness. Stiffness shows how hard to deform, how hard to bend. For example, wood is very easy to bend because E value of wood is very small. How about steel? It's 29,000 KSI, so it's very hard to bend. So that E has resistance of material to bending. And I is cross-sectional resistance to bending. So EI, if you have both of them, then it will represent how hard to bend. Okay, you can either increase E or I value to make your beam stronger, or both of them. Anyway, E is material property and I, moment of inertia, is cross-sectional property. Memorize it, and very, very important and fundamental. If you take second derivative of deflection, vertical deflection, then you are going to get m over EI. Memorize m over EI. We are going to use m over EI a lot in this chapter and from now on. So, in this chapter, we are going to use the relationship between shear force and bending moment when we draw bending moment diagram, and we utilize that relationship between slope and deflection. So you are going to link shear force as slope, bending moment as deflection. Memorize it. It's very, very fundamental. If you use integration, shear force and bending moment diagram has this relationship. If you integrate your load, then you are going to get shear force. This is your shear force. So that if you integrate shear force, then you are going to get bending moment. Yeah. The same relationship. Either one, if you feel one is easier to the other, then why don't you pick up? You can use either relationship because the reverse process of differentiation is integration. Okay, the same thing for deflection and deflection angle. Slope is deflection angle. So if you integrate m over ei, you are going to get slope. And if you integrate m over ei twice with respect to x, then you are going to get vertical deflection. You have to memorize these two relationships to continue on. As you see here, I defined v as vertical deflection and theta as slope or deflection angle. So that we are going to use analogy between shear force and bending moment diagram for the relationship of slope and deflection. Okay, now let's have a question in mind that, okay, what is a conjugate beam? Conjugate beam is an imaginary beam, not a real beam. It's totally imaginary. But any real beam will have only one unique conjugate beam. For example, we have this real beam and its conjugate beam is this. It looks pretty strange, right? But there is some regularity, and we are going to find the rule and learn. And for real beam, there is a bending moment diagram. I told you that you must be very good at bending moment diagram to start structural analysis this course. Okay, let's say you have real beam and you are able to draw your bending moment diagram. And m over ei diagram is nothing but your bending moment diagram divided by ei. Usually ei is constant of the beam, so that ei is very big number, but those are usually constant, unless you have tapered beam or stepped beam, which is not usual in undergraduate courses. So anyway, please note that bending moment diagram and m over ei diagram is exactly the same in shape, but scale is different because you are going to divide m with ei, which is huge number. Okay, but we are going to compare slope with shear, deflection with moment. Okay, how you come up with conjugate beam for a real beam? What you are going to do is you are going to switch your support condition and memorize it, because this is simply a technique, so that there is no analytical proof for that. Pin will be replaced by pin, so that no change, right? Roller will be replaced by roller. Again, there will not be change. How about fixed support? Fixed support will be free end. As you may expect, free end will be replaced by fixed support. If there is an internal pin, Okay, the member is continuous, but support is below that, underneath that. We call it internal pin or internal pin support to be exact. Internal pin support is replaced by internal hinge. Internal roller or internal roller support is going to be replaced by hinge. How about internal hinge? Internal hinge is replaced by internal roller support. There are several, but if you memorize 2 or 3 things, then you can find the rule. So you are going to use this table to convert the real beam to the imaginary beam named conjugate beam. Pin support, no change, roller support, and fixed support to free end. And free end will be replaced by fixed support. Internal pin support, internal hinge. Internal roller support, also internal hinge. Internal hinge will be replaced by internal roller. Okay, let's learn through quiz problem. The real beam is given at top, and we are going to try to find corresponding conjugate beam. Again, one real beam has only one unique conjugate beam, so there is a one-to-one relationship. Okay, first, let's go from left support to right. We have 1, 2, 3, 4 supports. Fixed end must be free end. Free end, free end, free end. So that B is ruled out. Internal hinge will be internal roller support. Okay, and internal roller support will be internal pin. So my answer is C. And the last one, just as checking, pin support will be no change. So that C is the answer. This is conjugate beam for the real beam. Okay, one more quiz. Which one is conjugate beam for this real beam? Let's go one by one. Again, support condition. Fixed will be pin. You already got the answer? Okay, let's check the rest. Internal support, internal pin will be internal support. Internal pin will be internal pin support. It could be internal roller support or internal pin support. But I recommend you to use a roller if possible. But in FE exam, if pin is given, that could be answer too. So in FE exam, if you do not have roller here, do not give up. Okay, it could be pin. And roller and pin will have the same effect as long as gravity load is concerned, right? Okay, and here we have fixed end, so that must be free end. Okay, so that my answer is C, conjugate beam. So that real beam and conjugate beam has one-to-one relationship. Again, only one unique conjugate beam is there for one real beam. Okay, so what? Conjugate beam method has two rules. As I already explained, slope at a point in the real beam is numerically the same as shear force in the conjugate beam. So instead of calculating slope in the real beam, we are going to calculate the shear force in the conjugate beam. Because I assume that by now you are very good at shear force diagram and the bending moment diagram. So instead of slope calculation or deflection angle calculation, why don't we calculate the shear force of the conjugate beam? And second, deflection in the real beam, very hard to calculate, yeah, I admit. Instead, we are going to calculate bending moment in the conjugate beam. That is what we are good by now. So we are going to use these two theorems to calculate slope and deflection. And you will see that conjugate beam method will be used very, very widely in depth in the subsequent chapters when we do slope deflection method and moment distribution method. So without knowing this clearly, you cannot continue on. Okay, again, in summarize, there is a real beam here, and we are supposed to calculate slope and the deflection of the real beam. Then we are going to come up with its conjugate beam, which is imaginary beam, it's not real beam, by switching the support conditions. In here we have fixed, then free, internal pin, internal roller support, internal roller support, internal pin, free end, fixed end. That's it. And then, okay, again, we are good at drawing bending moment diagram, right? And bending moment diagram of the real beam. And the shape is exactly the same, but we are going to divide the bending moment value by EI. Okay, again, E is material stiffness and I is cross-sectional stiffness. So shape is exactly the same, but not actually exactly the same. They are similar. But M over EI is a lot smaller than M value. Anyway, we are going to apply M over EI as a load to your conjugate beam. And then we are going to calculate shear force and bending moment one more time. Then you are going to see that slope in real beam is shear force in conjugate beam when you apply M over EI as if it were load to conjugate beam. So that we are going to call M over EI as conjugate load, and we are going to apply the conjugate load to conjugate beam. In that case, we are going to get slope and deflection as shear force and bending moment of the conjugate beam when you apply conjugate load on the conjugate beam. Okay, example problems. This example problem was taken from textbook, and we are going to deflect maximum deflection of the steel beam. It may look very simple, but actually it's not that simple. Even though conjugate beam is the simplest method and a very convenient and popular method among engineers. And I really like this method and I use it a lot for real situation and also when I derive or prove something. Okay, when a real beam is there, first step, we are going to come up with a conjugate beam. I'm going to get a bending moment diagram first. I'm going to draw a bending moment diagram and the shape is like this and the value is 3 by 6, 18, or if you take left hand side free body, 2 times 9 will be 18. And I'm going to have a triangular shape like this. Okay, that is my bending moment diagram, and that is positive. And you will see that why I asked you to put positive sign all the time, positive or negative sign on your bending moment diagram and the shear force diagram. Okay, and we are going to convert real beam to conjugate beam using this table, which must be in your mind by memorizing it. Okay, let's switch the support condition. Pin will be pin, roller will be roller. Okay, then M over EI diagram. M over EI diagram is again same shape as moment diagram, and we are going to divide it by EI. That is my conjugate load, so that I have a conjugate beam with conjugate load, which is moment divided by EI. And one thing, most students make mistake here. First mistake here, when your bending moment diagram is positive, my conjugate load will go up. If it's negative, my conjugate load will go down. Memorize it and don't make mistake. M over EI diagram is positive, then the load go upward. Okay, now I have my conjugate beam with conjugate load, right? And I'm going to draw my bending moment diagram for the conjugate beam with conjugate load. To do so, I need to find reaction first, because in this case, my beam is not in equilibrium because I have no reaction calculated yet, so that do not jump into to draw a shear force diagram and then bending moment diagram. Always calculate reaction first. When you have triangular load, it's best to get your resultant. Always dashed line, because those are not real load. Your resultant is nothing but area of this triangle, which is 81 over EI, 1 over 2 times 9 times 18 EI. That will be 81 EI. And for this triangle, we are going to have 27 over EI. And if you calculate your reaction, it will be 45, 63 over EI. Those are reactions. Now, my conjugate beam is in equilibrium. Okay, again, conjugate beam is an imaginary beam, but make sure that your conjugate beam also in equilibrium. Very, very important. Okay, where the maximum deflection occurs. Okay, and in any math function, including bending moment diagram, when your slope is 0, your function will be either maximum or minimum. So, for a function to be maximum, it must hit horizontal slope. It's like you go up mountain and hit horizontal and then going down. So that maximum deflection occurs where slope of the real beam is 0. And that is general, 100% of true for any function, except including deflection curve, elastic curve. Maximum bending moment of conjugate beam will occur where shear force is 0. We learned it when we studied about bending moment diagram, right? So that I'm going to look for where is zero shear. A zero shear point is very, very important to engineer. So important because our job is to look for bending moment, maximum bending moment, right? So where maximum bending moment is, that is so critical to me to engineer. And then where is it? We are going to look for where shear force is 0. Because maximum bending moment location is very hard to locate. So that instead we are going to look for the 0 shear location. Then at the same spot, maximum bending moment will occur. Okay? Alright. This is my bending moment diagram, the left hand side. And I'm going to assume that maximum bending moment occurs within left hand side. If I'm wrong, then when I get the answer, I'm going to check right hand side. But most probably, maximum bending moment will occur on left hand side because it's longer. Okay, and I'm going to cut the beam somewhere here where my distance is x. Because I do not know where it is, so I'm going to show it as x. If x is unknown, the magnitude of, intensity of my omega here, from here to here, is unknown too. Then how can we find x and omega, both of them? How can we find it? We are going to use similarity of the triangle. Because large triangle was given as 9 feet and 18 over EI. So that we have this relationship. Omega over x is same as 18 over EI over 9 feet. We have similar triangle. So that omega is this. Okay, now that the resultant of that load, triangular load included in x, there will be 1/2 times height. 2x over EI times x. 2x over EI times x, and half of it, there will be triangle. So that if you get shear force at this x location, then 45 over EI going down, negative, and the resultant of triangular load going up. This must be 0. So that if you report to your calculator, then you are going to get your x value as 6.71. And this is actually all math, not real structural engineering. Alright, anyway, I found 6.71 from previous page, and the resultant of the triangular load and reaction. So my bending moment is nothing but 45 EI times 6.71, and the resultant of triangular load and 1/3 of 6.71, because here my centroid, there will be 1/3 from higher side of triangle, and my bending moment must be 0. Then please make sure that this bending moment of conjugate beam subjected to conjugate load is nothing but deflection in the real beam. So if you simplify this equation, you are going to get this. Okay. On the previous page, I've got this value. And if you plug in EI, which is given, then you will see that 10 to 6 and K is 10 to 3rd, right? 10 to 3rd. So that 10 to 9th will be gigapascal. Newton over meter square is nothing but Pascal. And this number is to convert millimeter to force to meter to force. Millimeter is 1/1000th of meter, so 1000 raised to force will be 12. So if you carefully type in, you are going to get this value as meter, but we are going to use millimeter or inch as unit of deflection, because that is practical value. The meter deflection never will happen. The feet deflection will never will happen. So millimeter deflection and some fraction of inch deflection will occur. And please make sure that the negative sign indicate deflection downward. So this is the answer. And when you type all these things to get this value, you will see that you frequently make mistake. But don't worry, just go over the same equation several times, a couple of times, then you will get familiar with how to handle these complicated numbers in your calculator. So we calculated maximum deflection in the beam.